Speaking of which, so I think, Elena, you were asking about this guy right here. So this is kind of a neat one because we can get a lot done in one setup of dist fill. Now, I'm not going to tell you what homework this came from, and don't look at the address bar above. And then you all did. Awesome. So, how would you know, first of all, what kind of problem is this? Good. How would you know, even if the address bar wasn't up there with 7binhw.html? How would you know? Haley, help me.
It gives you a fixed number that you randomly selected.
I've selected 10 people.
Yeah.
There's a percentage, 85%. You don't see the word normal distribution. That's kind of a dead giveaway.
But we can assume that some 85 do have it, but like 15 don't.
Exactly.
Right.
And there's your do or don't. That's your binomial. You can assume the 85% is constant because you're selecting 10 out of Americans. Like Max selecting his 4 out of chickens, thousands of chickens. This is even more ridiculous, 10 out of many, many, many millions of Americans. Perfect. So the first question I have, does it represent independent or dependent sampling?
Independent.
Arguably independent, absolutely, for that very same reason. Arguably independent because you're not changing the 85% by removing 10 of them. You'd have to remove a lot of them to change it 85%. Okay, what's the chance they all have health insurance? Notice these next few are all probabilities.
Yes.
All probabilities. What am I going to have to do to get the probabilities?
TI.
You're going to run your TI, you're going to set your distribution up, you're going to get that distribution from the calculator. Yes. By and large, let's switch over to the TI. There we go.
This is the binomial?
It's not called binomial, it's called dist fill, which is
the homework.
Oh, yes, you did
Binomial.
look at the address. Excellent. Yes, this is the binomial homework. Yeah, we're doing it looks like E4 through probably E12. The whole shebang. Proud of you, Haley. Kidding. I'm not proud of the rest of you. One of those psychological things. Don't do this. It's like mountain biking. Look where you want to go, not where you don't want to go. Look where you don't want to go, you go right where you don't want to go. So program, dist fill, starter up. Now we selected 10 Americans.
So smallest would be 0.
Smallest is going to be 0. Pretty much binomial always starts at 0. Largest?
10.
All of them, right. So basically your smallest is always 0 and your largest is always how many you select. 0 to n if you want to use the stat lingo. Make sure we can see this.
Probabilities.
Yep, I believe so. We're going to go 0.85. Yep. And then you go select binomial. Let me ask the question while I got you here. Did you guys ever use these two options? Or this third one? Yeah. I might rewrite the program so it's just binomial because it seems like that's the only time I really use it. I wanted to make it more multifaceted, but we seem to never use the other ones, so I might just rewrite it. Okay. Good to know. Probability of health insurance in one person is 85%.
Yep. 0.
It is now done. The distribution is waiting for you. So now it's just a matter of answering the questions, picking them off one by one. We'll flash back and forth between the screens. Okay, so back to the computer screen. First question is, what's the chance they all have health insurance? Oh, you know what? I want to do one more thing. Let me do one more thing, and this is nice. I cleared the board. Let me define the random variable that we're talking about. I think this is pretty important, okay? So we now have a distribution. You don't have to do this in your notes. I think it's nice to see it, though. We're defining this as the number who have insurance out of 10, and then the probabilities. So this clearly goes 0 up to 10, and this you get from dist fill. And I think this is important because we're talking somewhere in here about insured, maybe uninsured. No, we don't talk about uninsured, we talk about insured, or does not have health insurance. And it's important to know the numbers in the left column, what they are, whether it's those who are insured or those who aren't insured. So we did it as insured. If you did not insured, you'd put in 0.15%, and you'd see a cool distribution change. There's a neat distribution difference. They're alike and they're different, and there's some neat ways, but we'll get into that later if you want to. So, the chance they all have health insurance?
You just look at the 10, right?
Yes! We just look right to the 10. Let's switch over to the document camera. Let me move this off to the side a little bit so we can make room for it, make this all fancy. So you go to Stat Edit, and we go find, I'm going to clear L3, that's getting in the way. Okay. There we go. There's about, call it 20%. About 20% chance they're all insured. That's pretty low, huh? Pretty low. More than 5. Now, why is it so low? If 85% of folks are insured, why so low?
There's only 10.
Good. You got to remember, 85% gets exponentially smaller as you apply it over the 10. So the chance that 1 is uninsured is 85%. The chance that 2 out of 2 are uninsured is 85% squared. The chance that 3 are uninsured is 85% cubed. 4, 85% to the 4th. And what happens as you keep applying those 85%? Keeps going down. Just like the more birds you buy from the farm, the less of a chance they're all girls. The chance that you get the rooster is going up with every bird you buy. Because every time you buy a bird, 90%, 90%, 90%. So this is the chance of all girls. It gets pretty good. There's a pretty good chance, almost certainty, that you're going to have a boy in there somewhere past the point. So this is, everything binomial is chickens. But it hasn't really good value.
So 20%.
20% chance that they're all have health insurance, which means there's an 80% chance at least one doesn't. Oh, I bet you I just answered the next question. I bet you I just answered the next question. I sure did, didn't I? I just answered E6.
So
Isn't E6 the complement of E5? Because either they're all insured or they're not all insured, and not all insured means that at least one doesn't have health insurance. What I try to do with this set of problems here is to throw back to your first couple projects and the idea of at least and all, that complementary idea. The opposite of them all being insured is that at least one is not. So if we got 20% for E5, that means the other 80% are in E6. It doesn't break it down as to how many of them have each. That's what we're getting to next, I think, is the rest of that. Is that believable?
So it's 80%?
Yeah, 20 and 80, or 19.6 and 80.4,
So
whatever you want to break it down.
Half of them, again, we are looking at.
Oh yeah, we'll get to E7 here too, yeah. Half of them, so that's 10, right? We have 10 total, which means that we got 5 of the 10. So you're just going to switch back over to your distribution. Yep, switch back over to your distribution. Half would be 5. There. Pretty crappy chance, less than 1%. Less than 1% chance that half of them have health insurance, which hopefully makes sense. Again, it should be 85%, not 50%. So seeing 50% in your sample should be a pretty low percentage. Fair enough? Ish. Cool. Hey, getting there.
So that's average.
That's E7, I believe, right?
Yeah.
What's the chance? Right, half of them have health insurance.
So like 0.8%.
Yeah, 0.8% sounds good. Yep, I'll buy that. E7, yes. Sorry about the flip-flopping on the screen. It seems to be the best way to do it, I think. Cool? Let's go back.
That's interesting question, E8.
Find the most likely number of them that has health insurance. So I'm asking you to find the mode, but in a probability context. Jordan?
So
just finding the one that has the highest percentage.
Yep, that's the most likely. Remember, probability is likelihood. Probability is average occurrence relatively frequency. So you have to go look at the relative frequency, so we're going back to the TI, and just scroll through and look for the highest probability. So let's do that. I think we see it. It's right there. 9 is the highest. 9 out of 10. 34%. Almost 35%.
what was the question most likely?
What's the most likely number of them? So the most likely is 9 insured, which would then mean 1 is uninsured. 1 is uninsured and 9 are insured. So this is kind of like when you start buying chickens and chickens and chickens and chickens and chickens in vast quantities, eventually a rooster pops in. Even though a rooster is unlikely in one selection, over time the rooster becomes more likely because there's more ways for that rooster to work its way into the flock.
Okay.
Believable?
Yep.
Guys find us? Okay, good. Okay, flip back over. Let's see. Not the average. We'll do E9 and E10 together. The average and the standard deviation around that average. Now there are cutesy little formulas for this, and I'll happily put them on the board if you want to, but the easiest way, Jade is already going for it, what's the easiest way to find the average? As it has always been? 1 bar stats. Well, add and divide, David, that's the easy shortcut, but even easier if you have the distribution in the TI. 1 bar stats get you all the numbers you need, and you'll see right away what formula you could use if you want to. But I personally don't think the formulas are worth memorizing. So, stat calc, 1 var, just make sure you put in L1 and L2 because it doesn't know that. It doesn't know your data's in two places. Well, your data's in one place. Your frequencies are in L2. Coolio? There we go. We should have 8.5 on average, which again, if 85% of 10, that's 8.5. And that's the shortcut formula if you're interested in it, and it's okay if you're not. Which standard deviation do we use? I love this.
The only one that.
The only one that comes up. Why is this one not there?
Because it's a probability.
Because it's a probability distribution, which means it's the entire population. It's a probability distribution. This is different than a frequency distribution. A frequency distribution is just a collection of data, which is probably most likely a sample. But this is a probability distribution, which means that everything that could possibly happen is accounted for. And that's rad. Therefore, there is no sample standard deviation. That's one answer. That's my favorite answer. The other answer is the formula is undefined with n equaling 1. But that's a mathematical answer. You guys like mathematical answers. Please, Elena.
So how would you want us to run? Because you
I'll tell you.
say,
I'll call it 1.13.
you'll say.
I'll put it on there somewhere. Yeah. I'll put it in there somewhere.
And if we're close, you.
Of course. That's like I said over here with this one, Haley, if you got to the point and you're there, it's like she forgot the 6,000 but whatever.
Yeah.
I'm looking for big pictures here, not small pictures. So.
Unlike other math classes.
Well, in other math classes, that level of precision is kind of guaranteed.
Yeah.
You don't get that level of precision in a stat class. And you shouldn't in life. I mean, think about, you guys ever build like a shed or a fence, you're putting a fence in and you're like, you put the piece of wood down and it's off by an inch. Do you go get a new piece of wood and recut it? No, you put your shoulder and you bend it, and you put a screw in to hold it in place. I mean, that's statistics.
Right.
You make it work in the margin of error. Now, eventually the piece of wood gets too long and you can't do that. It's outside of a competency. Lop off a little bit, shove it back in. But the lopping doesn't have to be perfect. It just has to be ish. And that's what I'm after too, I'm after the fence, not these perfect pieces of wood. I'm not a craftsman when I any stretch of imagination. Okay? Good so far?
Yeah.
So what do we put for that then?
Oh, sorry. It's just your average
Yeah, the average 8.5.
and your standard deviation.
Oh.
Yep, that's it.
Do you want us to put plus or minus 1.1?
You don't have to. You don't have to. I'm going to have you use that idea on the exams where you're adding and subtracting usually 2 standard deviations.
Oh, okay.
So I'll have you dealing with that. You know, it's not wrong to put it. It's not wrong not to put it. So your choice. Your choice. Cool. Excellent. Let's switch over to the computer again. Whoops. Next question is 11. 95% of the time, at least how many are insured? This is an interesting question. Okay? 95% of the time, at least how many people out of 10 are insured? Okay, so what makes this question hard is not the math, it is not the stat, it's the English. It's the word at least how many are insured. So what we're going to do is we're going to switch back over again. It's all about the distribution again. We have to look at the
So
calculator.
you're just putting 95%?
We basically have to find, let's go back and look at this.
Yeah, let's see.
So, we know, let's go to the end here for a second. Just because we started here, we know that basically 20% of the time, they're all insured. All of them are insured 20% of the time. If I back up, this tells me that 9 of them are insured 35% of the time, which means that 55% of the time, at least 9 are insured. Let's back that up, make sure we catch that. 20% are insured, 10 are insured 20% of the time. 9 are insured 35% of the time. So, 55% of the time, at least 9, if not more, are insured. Is that fair?
Yeah.
So let's back up a little further.
So keep adding.
Let's add 28 in there. Okay, 28 plus 55 gives us, 83?
Sure.
83% of the time, at least 8 are insured. And that looks like 95, doesn't it?
Okay.
95% of the time, at least 7 are insured.
So that's,
Is that fair?
Yeah.
That's all we're getting at. It's like a reverse percentile, if you will, ish. But that's important because imagine you're a manufacturer of like a battery or something for like a hybrid technology car. You can guarantee 95% of the time this battery's going to last 16,000 cycles or something along those lines. That's important to be able to say something like a low-end estimate. A low-end estimate. More on this in 244 for sure, but that's how you attack it with this one. Is that fair, friends?
yes.
You guys buy that logic? Go ahead, Elena.
What if you need not to find 95, but the least percent?
Good, good. Well, when you say least percentage, like,
Whatever, 1%.
well, then you just keep going. You just
And
basically.
do it.
Now the problem with it is
Yes.
they might not land exactly like this landed essentially at 95% and cut 5%. So then you'd say, okay, you can make it linear. Let's say you want to say at least 90%.
Okay.
Well, then you come down to here and you're at 83, and then you say, okay, let's take half of these, half of that. Now we're roughly at 90. So you call it like 7.5. On average, 7.5 will be insured. Which again, it's an average. So it's okay to say 7.5. I promise you not to, just so you know.
But what if you
I'll
have,
find
for
numbers that
example,
are
again,
nice.
like in my situation, like -4, I mean like the scientific notification, which is.
Oh, these guys up here. Let's get to that question next.
Okay.
Let's answer that question next because I happen to look ahead and I noticed that E12 was what is an unusual number of. And that's where that scientific notation comes in.
Uh-huh.
So basically, what I look at, this is my, when you hear the word unusual, what do you think of?
Extra.
Yes, outliers, extraneous data. That's a good word. Extraneous data, outliers. Right? You're looking for the ones that shouldn't happen. That's what makes them unusual. Now, when you look at the distribution, here's the distribution right here. Okay? Is this unusual?
No.
20% is not unusual at all. That's why I was so surprised. That's essentially the percentage of induced labor. Remember? About almost 20%. It's not unusual, which makes me go, what the hell? Why are we inducing at such a high rate? Anyway, more on that later. Is this unusual?
No.
Is that unusual? Is that unusual? Is that unusual?
No.
Is that unusual?
Actually, no.
So-
It's around one, I think one.
Now, this depends on how you define unusual. I tend to default to any probability under what? Do you remember this?
5%.
That's what I tend, Mimi, thank you. That's what I tend to default to because that's what's used in stat journals all the time. So if it were me, and this is me, my definition of unusual, I would call anything from 6 down unusual because they're all under 5%. 4 is under 5%, the rest of those are way under 5%. But that's how I define it. Elena's saying she defines it under 1%. Totally fine. That means if it's under 1%, 6 is okay, but then 5 is unusual because it's 0.8%. So it depends. Remember what I told you guys about outliers? There's not one definition of them. There's not one definition of them. So I promise to not have an outlier question on the in-class part of your exam because it'll wreak havoc with your mind. Crap! I thought he said I can put anything I want here for an answer, but that doesn't seem right. I promise not to do that to you.
Okay.
But just realize that's how you, I like questions like that because think about it too. We said 95% of the time, at least, well, 95% of the time, at least 7 are insured.
So it'd be 6.
Everything else is unusual because that adds up to the 5%. So the 6 and down are all unusual. And Elena mentioned the scientific notation. Don't get too freaked out about that. When you get down to here, like this last one,
Yeah.
all that means is 0.0000003.
Yes.
It's ridiculously small. There's a chance of selecting 10 people, none of us, that's 1. I didn't go to 0, did I? There. There's a chance of selecting 10 people and having none of them insured. But it's a really, really, really small one. So it's possible, but not probable.
So
Love
what
that.
would our answer would be something like a number in L2
For what? For what question?
for E12?
E12 is just,
Unusual
no,
one?
that's a good, this is a good question,
Yeah.
a very good question, thank you. If I asked what would an unusual number of people be to be
A number
insured,
of people.
that's
okay.
right, my friend,
There we go.
good. And that, you asked me a question similar to this a couple weeks ago, Haley, I remember, made a big deal about it, and I'm gonna make a big deal about it again right now. It's important, that's why I wrote this on the board right now. This is my Haley reference. Because it was very important, I forget that as you guys are learning these T-tables, there's a disconnect between what you're seeing and what you will see as it becomes more comfortable. This is your data,
Yeah.
and these are the weights. This is how much to count your data. So when I ask about the data, I'm talking about the numbers in this column.
Right.
Yeah, this helps you answer the question. But I'm talking about those numbers, and not to make a huge deal, I don't embarrass you, but it's amazingly important to differentiate between that, what you're looking at in both columns. So,
Okay.
thank you for bringing that up again, I appreciate it. Cool? Yeah, David, go!
Why did I have in my head that outliers were uniformly outside of 2 standard deviations?
Well, because that's one definition of them. If the data is
Well,
bell-shaped. The problem with this data It's definitely not, yeah. The problem, and this is one of those rare times, oh, you can't see this. Yes, you can. This is one of those rare times where we can use disk draw. Remember this program I also gave you back in the day? Back in the day, I gave you like 5,000 programs. So when you do disk draw, there, that's the problem with that. It's kind of skewed. So when you got bell-shaped data within 2 standard deviations is 95%, which puts 5% unusual. But the problem with this is it's not bell-shaped. Now in 244, we've got tricks to deal with this. We lop off the part at the end that's not bell-shaped and treat this part like it is with certain corrections. And we'll get to that. Does you take it 244? Those of you not saying, hell with you, I'm not going to do it. That's fine too. But there's all kinds of... So basically, the reason I like the 5% rule is because it works for anything. You could also go with IQR, couldn't you? You go with modified box plot, right? Draw a box plot. Let's see if that'll work. It might make the TI fart out, but let's just see out of curiosity. L1, L2, right? Yeah. Look at that! 0, 1, 2, 3, 4, 5, 6.
Weird.
There's all your unusual data points, which means 7, 8, 9, and 10 are within the realm of possibility.
So actually,
Love it when a plan comes together.
we can actually check ourselves like that, right?
Yes, of course. And when you say check yourself, I want to caution you against this too. These won't always agree perfectly. The definitions of outliers don't always agree perfectly
But
with
that's
each
what
other.
I'm saying, ish.
Of course, but when you say check yourself, if you get a slightly different answer here than you did there, doesn't mean either one's wrong.
Okay.
It just means that, just like you saw before, an outlier is not always an outlier depending on how you're identifying it. But I just love that's freaking
So you
gorgeous.
can put like 0 to 6 people.
Yeah, 0 to 6 people, exactly. From 6 or less, yeah, for sure.
Okay.
Cool? Yeah? How you feeling? Yeah? You guys gonna crush this.
I have,
Yes, Haley, go!
it was on.
Oh, yes, the quiz, yes.
Yeah.
Let's just fire up the quiz
Okay.
and take a peek at it. Back out to the week 10 quiz due. So this was, oh, you can't see that. Here was the quiz we had due for today. There it is. Let's see if I can make it, can I shrink it down? There's a zoom on here somewhere, I know, right?
Right there.
Oh, I just saw it. There it was.
Yep.
Nice. Then can I do? Oh, I made it worse. How's that? That's okay. So I didn't mean to make this horror-inducing for you. All this was to just to get you into your program and make sure you're using your TI effectively. That's all this was. So when I said, what's the chance that you grab a z-score bigger than 1.96?
That's going to be a forward, right?
It's a forwards. Why?
Because it's giving you a raw score.
Because I gave you a score. Exactly. I gave you a score. So let's mute this down. Go over to the TI. Let's erase this. You don't need them right now. So I'm going to draw a picture for each of these. I'm going to draw a picture for each of these so you can kind of see what's going on. So this is quiz number 1. So
Can we get our quizzes and compare it to what you're doing?
can
Can I
you
take
do?
my quiz if I get it wrong?
Yes, you may. I'm feeling generous. It's the last day of the term.
Grab your quiz.
What number's in the middle here?
Uh,
0, because it's standard normal, right? Standard normal. And you got a plus or minus of 1. You can grab your quizzes if you want to. That's totally fine.
I'm just comparing.
You just compare. That's fine too. I'm feeling generous. What the hell? It's the long term.
We can't do
You
that?
guys have worked your ass off for me. So now, the point is, all right, go ahead and grab your quiz.
Yeah. But
That's totally fine. Grab your quizzes.
then you can put it back.
All the way back up.
Compare.
Yeah, what the hell? Why not?
sorry, maybe I should ask a different
Totally
question.
fine. Yeah, it's fine. It's week 10. It's all good. It's all good.
I'm pretty sure I got it dialed.
I'm sure you did too. I'm sure you. I tried to make the numbers really nice on this one. I went out of my way to make them nice.
I think just what threw me was it says
Bonus,
like
we
greater
can grade
than.
it.
I know. Well, and thank you. This is why I'm drawing the picture.
Okay, yeah.
So basically, we know that the z-score is 1.96. It's to the right because it's positive.
Right.
So the question is, I want to know what's the chance I get a z-score greater than that. So give me a z-score greater than that.
2.
2. So 2 would be like here. Give me another one.
2.5.
2.5. Another one.
4.
4. Another one.
A million.
A million. Give me another one. I mean, actually, it's got to be out on the street somewhere if it's a million. But give me another one.
1.1.
So you see what the point? No, the 1.1's over here. That's
Oh,
nice.
the one.
How about 2.1?
Yeah, 2.1, yeah. Exactly.
How about 2.2? How about 2.3? 2.4? You see what I'm doing here, friends? This is why you need the Binomial program or some other way, because you have to get all of those z-scores that are bigger than 1.96. and there are infinitely many of them, from 1.96 off to infinity, and that's the trick. You can't do an xp of x column because you'll never be done writing it. But that's where the normal comes in. So you grab your TI program, it's the normal. The biggest key is realizing it's a forwards problem.
Right.
Because you have the z-score. You have the z-score, so it's forwards. Is it between left or right?
Left.
It is, well, you could do it left, you could. You could, but then you have to do a convert. I think it's easier to go right.
Is it because it's greater than?
It is. And what I've worked at for years is to try and come up with a way to explain that symbol, and I've never come up with a good way. That's why I always go back to drawing the curve.
Yeah.
Because people understand what greater than means, but the symbol greater than, they often reverse. They get it backwards. So we're going to go greater than, so it's to the right. So you know what? Here's an easy way to remember. Look at the way the arrow's pointing. That's the way you're shading. How about that? Z bigger than 1.96, you're shading to the right because the arrow's pointing to the
I
right.
think you learned that in like